Is fusing Apache Spark and Lucene for near real-time predictive model building. So I did want to do a demo, but thanks to Casey, I'm not taking a risk. You can see me after the talk, and we can do a demo. So this is a joint work between me and Pramod, and we have contributors from multiple teams, platform, algorithm, front end. So So first, let me give you something more on the data sources that we have, right? So we have made use of two kind of data sources. One is a location data, and in that what we really have is we define a source IP as a unique row key, and on that source IP, we get the approximate location of each of the source IPs. Now, by approximate location, I mean the latitude, longitude, duration, time zone, and all of that. See, we are a phone company, so we get all the data from phones, and each phone has a source IP with it. So we get the location for the source IP. We also get the location and the clickstream data for the source IP. So what do I mean by that? Is if you know network protocols, so this is the data that phone collect as a IPFix or NetFlow format, and each of the clickstream record will have with it like the start time of the record, duration, HTTP host, which HTTP host this source IP is connecting to, or this phone, and you get the upload byte, download byte, what kind of HTTP method. Now, keep in mind that this is not a web server log. So one web server log can span into multiple network records. So it is a network data and not a web server log that you can get out of a Google web server. Now, based on that, I will explain some of the data model issues that we have, right? So if you have made use of any of the Mllib datasets or Mllib databases, you know that there are concepts like dense dimension, dense measure. So what it means is that, say, the schema of the data is source IP, and then on a source IP, you get a certain day, certain hour, which TLD this source IP is connecting to. In this case, it's Macy's.com, and which zip code this source IP or the phone number is at, right? So that zip code shows up. You also get visits, how many times in the whole day that particular zip code has been visited by the phone number. So in this first representation, everything is dense. So your dimension, which is TLD and zip, they are also dense. The measures, which you have visits, and they are also dense. Now the second version is a sparse dimensions dense measure, in which you get your TLD and zip code. They become a list, no longer a dense version, it's sparse. Now third category, sparse dimension, sparse measure. So both measures and dimensions become sparse. And this is like the most complicated Mllib representation that you have seen. And this is the data we have. So the data that we have can be represented as sparse dimension, sparse measure. And in this talk, I am focusing mainly on last n days, which is the n aggregated days of sparse dimension, sparse measure data set. So the competing technology in this space is PowerDrill. You know, it's a Google paper. They have it, but the code is not in the open source. Druid, LinkedIn, Pinot did the versions for sparse dimension dense measure. They don't handle sparse dimension, sparse measure yet. Oracle HBase or HyperIon, if you guys have made use of that, they can handle sparse dimension, sparse measure, but I don't know the distributed scale. And also all these are not free, and we wanted to keep all the things in open source. So that was our main focus. So now let's talk about that. How do we represent this document data set? How does a data frame translate to a document? So as I said, that we are focusing on a sparse dimension, sparse measure data set. So which showed up in the first schema. If I can make use of. So is there a pointer in this? Okay. Oh, nice. So yeah, so if you can see that this is what I talked on, that there's a TLD and zip, Macy's.com, Coast.com were top level domain, and this particular source IP visited them, and then also this zip code with certain counts, right, with visits on them. So now the source IP in data frame version becomes a primary key of the row. In the document version, what this becomes is a document ID. Now this TLD and zip, right, in data frame versions, these are string and sequence of string. In the document version, this becomes single value and multi-value field. Now keep in mind these are indexed field. By indexed field, what we mean that you can search on this field. So there will be a reverse index constructed on any field that are single value, multi-value indexed field. Now this visits and like TLD visits, zip visits both. So in the dense version, these are like a double numeric values. And in the sparse version, this becomes a map of string and double. And in this map, the string is basically the identifier from the TLD and zip. Now this particular representation in document view is represented sparse vector, and it's a stored field. So by stored field, what we mean that you cannot search on them, you can retrieve these fields. Now the distributed collection of this source IP in our world, like the devices or the source IP, the distributed collection of the source IP becomes RDD of documents. And these documents are Lucene documents. So now you can see that how we mapped from a row-based representation to a column-based representation that Lucene have through the document. Now in our experiments, as I will go in next, that we have scaled to 100M source IPs, we have 1 million plus terms, so which are the sparse dimensions. So this has been scaled to those numbers. Now, based on that, this particular slide shows what are we trying to do. So we came up with something called a device analyzer, and the high-level goals for this are it does search and retrieve devices that match a certain query that our front end comes through the front end to us. Now, what can we do on them? Once you retrieve the devices that match the query, we have provided capability to generate statistical and predictive models on these retrieved devices. Now, this is kind of the high-level flow chart, and it's color-coded, actually. So if you see the blue charts are basically the batch flow. So what does it mean? That to run both our streaming flow and the API flow, which will come next, we need to do a batch runs. And for that batch runs, it needs to be running at a fixed interval of time, like a day or 4 hour or 6. So this particular blue-coded diagram shows you the batch workflow. The yellow-coded diagram is the stream workflow. This is yellow, it is a bit slow, so that's why I showed it in this color. And what it does is that the browser page pushes messages directly to Kafka. It's a Kafka REST client, control goes back. And then what happens is that we make use of a streaming flow to read the messages out of Kafka. It makes use of something that we constructed in the batch flow, and it finally does basically the calculation we want to do, pushes the result onto HBase, and then an API exposes the output back. So the whole flow is yellow, and it's a bit slower. It's an asynchronous flow, while the third one is a device top K. So what it does is that it gives you some top K characteristic on a query that came in, and that particular query is represented by synchronous call. So means the control stays with it, and all of these 3 particular flows are implemented with Spark. Now to make it happen, as you can see, there are multiple components in this game. So we have to come up with something called Trapezium. What is Trapezium? Trapezium is an open source framework to build batch streaming and API services with Spark. Now the code is in open, you can go into the GitHub and look into it. So it has mainly 3 components. So it has something called a data storage and access. So this is our abstraction over multiple data sources that we have. Data can be in Hive, it can be in HBase, it can be Cassandra, and something called a LuceneDAO. Focus of this talk is the LuceneDAO, because of course we know the rest of them. Trapezium becomes a central controller that connects all of them. What does Trapezium has? It has a ETL, a common ETL and validation component. You can read batch data, you can stream data from a file system, from Kafka, from network file system, S3, through them. Validation is provided to you. It's just a configuration-based flow. And then you can implement multiple verticals. So you write your business logic in these blocks. And then, of course, you can have a common Mllib-based algorithm block, and which you can call. Now, the whole Trapezium architecture is designed as a configuration-driven flow. There are data sources that you can configure. Trapezium is your central controller. The output can be one of the data access storage layer that we talked. It can be Hive, it can be Lucene, it can be Solr. And then you write your business logic in these blocks. Your business logic is called various transactions. So the business logic can be written in batch, business logic can be written in stream, and each Trapezium gives you a way to test them in isolation. So we came up with this because we have some people doing ETL, some groups doing something else, so we wanted to have a common testing strategy for each group. And then finally, the architect can come up with the workflow to combine them, and he can write one test, and then the whole thing runs. Now, let's move into the LuceneDAO part, because that's the major focus of this talk. So in Lucene, we know that it's a scalable full-text search library. What it does, that your data comes as something like, say, Macy's.com shop, and this is a document ID 0. So what Lucene will do is that it will come up with these keywords out of this data. In this case, Macy's is one of them. And then it will store a reverse index on them. So it will say, it will store that Macy's has an index of 0, which is the document 0. Now, how we make use of Lucene in LuceneDAO? So we know that Spark SQL and Mllib, they are all row-based store. They are very much optimized for full scan, blocked operation, but they don't really support a column indexing. What does it mean? Simple, MySQL, you wanted to do a column search on columns. You can construct a secondary index, you can search fast. So how do we do it? So we needed to do that because our flow is real time, right? So we had some SLA needs. So that's why we did this Spark and Lucene integration. Lucene we know is battle tested. It's much older than Spark, much more respected actually. And what we really wanted to bring from Lucene is to add the column search capabilities to Spark. And then what we wanted to put on top of Lucene, we wanted to put a distributed shim on top of Lucene and support the Spark operators that we all like, right? Tree aggregate, tree reduce, map, all of them comes. So now what really is LuceneDAO, right? It builds distributed Lucene shards from the data frame. It saves those shards to HDFS or Amazon S3 if you want, for query processors. So some of the problems can be simple queries, make use of Solr for that. But make your Spark shards through Spark, it gives you the runtime, you don't have to run map reduce, right? And you can save them on cloud. Solr can access them. You can also access the saved shard through LuceneDAO for any of these machine learning pipelines that you have, which is the focus of our talk. Now let's go a bit into the Trapezium Batch workflow that I have shown. This is how you write a configuration. It's simple type safe configs. So in this case, you were saying that your data source is a HDFS-based source, and you were saying that this particular workflow, which I'm talking about this as an indexer workflow, this depends on one more workflow called aggregate. So what happens is that every time, every day, the workflow will be run. So the service always stays on. Each day it will run, and it will run this particular indexer workflow will only run if your aggregate workflow on that day has completed. If not, it won't run. Now, your business logic, you write it as transactions. So you were saying that, okay, I am going to write my device indexer transaction, and this input data takes device source as the input data source, which in this case is the device store data maps to this device store, which is a Parquet file. So right now we support comma separated file. We support Parquet, JSON, and all these things. If you are making use of comma separated files, then you can put a validation rules, and the common validation module will validate the data. You don't have to write any code for that. So now once your indices are generated in this device indexer code, then they get loaded into basically streaming workflow and batch. We'll come to those. Now, this is the indexing workflow's business logic. What are we trying to do? As I said before, we have a source IP, IP1. It went to Macy's.com 2 times on certain days, say, right? So this is day 1, day 2, day 3 data. Now what we are doing is that we are coming up with a dictionary encoding of Macy's, Walmart, Amazon, and then based on that, we are trying to come up with a sparse vector for IP1. So in this case, Macy's.com become index 0, and index 0 has visits 5 in last 3 days data that we have. So this is how implementation will look like. So you are implementing your device indexer business logic, you extend your batch transaction, which is supported through Trapezium, and then you write your process function, you construct the dictionary, and the transform function will construct the vectors. So all this code is already part of LuceneDAO. I'm just trying to, so I mean, you can look into this code actually. And then there is a persist. So what the process does is that it only does the processing and gives the control back to Trapezium. So you are not writing anything in the process method. You are giving the control back to the Trapezium, and Trapezium controls the write part. It will call the persist method, and you implement the persist method, and this batch time is a Trapezium supported batch time. So this gives you that this particular time the workflow has run, write your data with that batch time so that later you know that what was your last successful run or which the successful run have failed. Now if there is some sort of exception that is thrown back from process, so Trapezium will handle it. It will be a common handler for many different batch transactions like these, and you can specify rules, right? That if it is this transaction, Spark cluster is down, send something to your database, I mean, to your cluster manager to come look into it. If it is code level fixes, you can fix them. Now, this slide, I'm trying to show you the LuceneDAO, what is the indexing index size looks like, right? So in this case, basically, the rows are we are scanning through 1M to 73M, and this is the input size on the disk that is shown in this, and this is the index size. So you can see that we are making an index of the size of 267 GB, and data and index size is at par. So that is one more key thing, that you don't want your index to grow. So your data model should be smart so that your index size stays in control with the data that you have. This slide, I'm trying to show you the dictionary construction bottleneck. So basically, because we are mapping a dictionary, we are constructing a dictionary for each string index, a global dictionary. So as our number of rows grow high, more and more sites and zip code are visited by the unique row key, so the dictionary sizes goes up. Now the shuffle right from Spark, this particular shuffle has both that Spark needed from the shuffle needed from data frame operation, and it also have the shuffle needed to make the Lucene indices. So this is combined actually. Now this is a runtime plot of, as we scale the rows, you can see the runtime grows in a linear way, since we went like 1M to 4M to 8M. So runtime is at par, is scaling the way we wanted it. So this is a 20 executed 16 cores job, not a very big job. But it was fine for us, like the kind of runtime we wanted. Now, so this was the batch workflow, right? It constructed the Lucene indices in the batch path. Now I'm showing you the Trapezium API workflow. So what does that look like? So in Trapezium, API is also a configuration-driven flow. You can say that we support right now Akka and basically a servlet-based flow. Akka will be our default soon, I think, because this has been like all the non-blocking I/O that you want. So you just specify the host name, which is localhost, which port your API needs to run, and you say which is your endpoint and which class implements it. So that pretty much it, right? So you define your business logic in top K endpoint, and Trapezium will take care of running it, scheduling the API, and how to handle the exceptions and all details like this. So now how do you implement an API workflow, right? So problem we are trying to solve with API is to find top K. What does this mean? So given a query that comes like select all devices, select star from the devices that we have where the top level domain is Macy's.com and the city is say San Francisco or Brussels, right? The machine learning part of it wants to ask that find the top K dimensions that are highly correlated with selected device that the query picks up. Now the business intelligence version of this, very similar call, it says group by the top level domain, order by sum of visits, call it a TLD visit, and pick top K. Now you want to run all of these in 1 second on the data set that I showed. So now this is how a top K controller written with Trapezium looks like. So as you can see that there is a Spark context. So this is, we are making use of Spark as a service in this, and it extends a Spark service endpoint that Trapezium has provided you. Now you define the route. This route is Akka HTTP route. And then your route, the logic for your route is very simple. Request coming in as a HTTP request, and your response goes out. What do you do in the response? First, based on the request, you do a search. And this search gives you a data frame. It's no longer giving you Lucene documents. This is giving you the LuceneDAO supported. This DAO is a LuceneDAO in Trapezium, and the search gives you a data frame of device ID and vector. So this vector is the sparse vector stored field that we talked. Now, once you get this data frame, now you can see that you can run any of your favorite machine learning Spark pipeline that you can. We have to return this response back within seconds, so we had to do something more to make it fast. So I am writing is that get correlates. So what you really want to find out is the devices that match this search, find out the top K dimensions in them. And then to find this get correlate, you can make use of sum, support, mean, median, standard deviation, all the data frame operators that you want. Now in the Trapezium streaming version, right, streaming flow was a kind of asynchronous flow, right, because we did not want the user to wait for the response to come back. So for that, what you do is that we have a Kafka REST post, right? So this particular device analyzer compare augment, right? These are the two main algorithm in the streaming flow, and they are written with the Spark, with the Trapezium streaming workflow. And that also looks like a config-driven flow like this. So you say your data source is Kafka, that you are going to read these messages from Kafka. Now, just moving this Kafka to a file system or HDFS, you can move to a file-based streaming if you want, right? The core code logic is not going to change. And then since it's a Kafka, you give your Kafka topic details in configuration, and you again give a transaction, which is the device analyzer is the name of it, and this is your core business logic. And the business logic implementation of the streaming flow for compare, right? Let's see what is a compare. So the compare problem is basically you have been given query 1 and query 2. Query 1 says that, okay, same people, same devices who go to Macy's.com and stay in city San Francisco versus Macy's.com and the city of Brussels. So how these devices, what are the dimension that discriminates them? So this is the compare problem that we wanted to solve. Now, of course, to solve this, we have to write the business logic for that. Now, the business logic is written in process stream. Now, you can see that this process stream don't have any Kafka or HDFS, right? This is just a simple D-stream-based API, right? And you implement your logic like this. So what we are really doing is that we are again making use of LuceneDAO. For query 1, we get a group 1. So this is a distributed group of devices that matched query 1. Then we get the request 1, and we find the second group, right, which match to group 2. Now, both group 1 and group 2 are data frames now. and then you can run your favorite linear discriminant analysis that you want to run. So one of the things that you can run after this is that you can run this L1 regularized logistic that we have in Spark, and that will give you the dimensions that discriminates this to groups. Now, due to runtime requirements, we have to write our own. So we call it, if you know the weighted least square version, so we have a version which is faster than that. So we call it a sparse weighted least square, and we made use of Breeze quadratic minimizer to write that code. So it's just a runtime. Basically, we wanted a bit more runtime, but the results will match, actually. Now, in the streaming version, also you have a persist stream. Now, this persist stream takes a RDD, right? So what you do, you write your processing logic in process method, and in the persist method, Trapezium, the controller, will send each RDD from the streaming flow so that we know we can manage the exceptions the way we want it. Now, this code is all in 1.6. As we move in 2.0, you can see that both persist batch and persist stream will combine, and we will have a simple data frame, basically a data set based flow for the same thing. Now, Augment problem is a different variation of the same thing, right? So, but it's not, I mean, it's a variation of the compare problem in the sense that in this, we are given only one query that selects star from devices, where TLD is Macy's and City is San Francisco or Brussels. Now, in this problem, we want to find out the devices which are similar to this seed. From a set, because we have all the data with us, from all the data, we want to find out devices similar to the seed. This is known as a look-alike, actually. Find the look-alikes to the device. And then you also have to find the dimensions, which represent the look-alike, right? Rest of the flow, the process stream and persist stream are same. Only difference is the algorithm choice we made. So one of the key difference you will find is that there is something called DAO.search star. So this particular one gives you, LuceneDAO is going to give you all the documents now that matched, right? So this gives you the rest, basically. And then you were writing a one versus rest flow. And to write the one versus rest flow, based on the current request that came to you, you again do a DAO.search. It gives you the audience which matched the current request, and then you run your favorite look-alike algorithm that you want to run. Because now you got a data frame with all documents, you got one more data frame with the search that matched, then you can run your one versus rest flow. For this, you can make use of L2 regularized linear regression if you want. We have to come up with our own version to make it more fast. Now, as I'm saying that to do all this, we support something called the FastSummarizer, which gives you simple, like the summarization capability on top of the documents. So there's a sum support, sum squared, gram calculations, and then we have a solve. So this solve is basically L2 and L1 based linear regression solve. Now, major difference from Spark ML is basically we have to make use of array float for shuffle optimization. For level 1, we make use of Scala Java. For level 3, we make use of OpenBLAS. Now, this particular slide is the sync API benchmark. So this is the top K. Top K is a synchronous flow, means it's a blocking flow. So the data set is our full size data that I showed you. Now we are kind of stress testing the whole flow. So we are pushing 250 GB data on 160 cores, actually. And then we gave kind of decent RAM, nothing high, 16 GB RAM. And this is running Akka HTTP default cores, which is 24. Now you can see that I am scaling the query per seconds. So as I scale the query per second on the same Spark master, how does the runtime of the job looks like? So from 1 to 5, it's still like within 1.3 to 1.6 seconds. But as you can see, as the number of concurrent jobs are increased on Spark, we do see some nonlinear scaling, right? This is what we are looking into next. Actually, how can we scale Spark as a service more with the query per second benchmarking? So at one to 1.5 second is what our product has been asked for this. So we are okay right now. Now the async API benchmark is the compare, augment, the predictive algorithms that I showed to you. So these runtimes are also in seconds. So we are making use of same kind of setup, 266 GB data we are pushing onto 160 cores, nothing fancy in terms of RAM. So now this one makes use of fork join pool. So what we do is that we fire 40 concurrent requests onto the Spark node. And then in this, you can see the query per second scaling as well. The compare runtimes are 9 seconds for one, 13 seconds for two, right? And augment is more expensive. But since this whole flow is asynchronous flow, so user is not blocked and things are okay. So in 9 seconds, we can generate a predictive model. We can do train, we can do cross-validate, and we can do test and give the data back. Now, these are some of the functional details, how the top K looks like. So you define your audience, a Fox News, NPR, and then these are the top K site and apps. Now, this is one auto-enthusiastic segment. Now, this segment is defined as basically, this is your seed definition, devices who go to autoweek.com and caranddriver.com. And these are the top predictive segments. So you have fit a model, trained a model, cross-validated it, and after that, these are the top weights, the top feature weights of that model. And also you get the top, basically which zip codes are showing up high for the model that you fit. Now, most of you should know, this is a decile plot. Basically, this tells you that how good the performance of the model is. So what we do, we train the model on 60% of the data, and then on the 20% of data, we cross-validate. Rest 20%, we do the test. So this is actually the decile plot of how good the model really is, and we are doing all that in the 9-second runtime I showed. Yeah, I'm almost done. This last one. So now, this is the same slide for leisure versus business traveler compare. So these are the two audience or two segments defined by a leisure definition, people who go to Orbitz and Expedia.com versus basically people who are going to, say, Travelocity or Kayak.com looking for some cheaper tickets. And then how do they compare? So basically, what are the discriminant dimensions? So this chart shows you the discriminant TLDs. This chart shows you the discriminant zip code on the map. Yeah, I think that was my last slide. Thank you. I can take few questions. So we are data and artificial intelligence system, Palo Alto. So do join us and make machines more smarter. Thank you.
So, thanks everybody. If you have questions, please come down. I think we're a bit over time. Just want to tell you, we restart at 1:45 with the presentation you probably want to see. Ram Srihasha is going to talk about using the new API, the continuous streaming API for online learning. Thank you.